So this is the second problem of the in-class work covering chapter 5, and this problem we have two cylinders, a center one that's made of copper with some given information on it, which is the modulus of elasticity, the alpha, which is our value, the thermal expansion, and then our area, and then also the same information for our steel, which the steel is the outer ring. In this system, we have the two rings, and this we look at this view here, and we have the two rings that are being subject to a load of a rigid plate. Also, there's in the problem statement it says the system undergoes a temperature change of plus 10 degrees Celsius. So first there's a temperature change, and then second, the rigid plate applies a loading of 40 kilonewtons. So first thing we need to do, they give us our alpha values for each of these. So what we can go ahead and do is just write with the given information what we know, is we can determine our change of length, or our delta is going to equal alpha multiplied to the original length of a member multiplied to the change of temperature, right? So we know two of these, but we don't really know this, but we can write it in terms of our original length because they're the same length originally. So what we can do is just write for the copper, we can just go ahead and say the change of length for copper is then going to equal alpha multiplied to L multiplied to delta T. So that's going to be 17 times 10 to the negative 6th multiplied to our length multiplied to 10 degrees. And so the change of length for the copper is then going to be, doing the calculations here, 170 times 10 to the negative 6 multiplied to L. And then the change of length, doing the same process, our change of length for the steel, right? It's going to be alpha multiplied to L multiplied to delta T, and that's going to equal 12 times 10 to the negative 6 multiplied to L multiplied to 10, and then this right here, change of length for the steel is then going to be 120 times 10 to the negative 6 multiplied to L. So now what we know is we've just determined basically how far our shapes have shifted up, right? Our system is moved up, each piece, right? Because we have both steel and copper, right? And both of them have deflected upwards a certain distance. And so if you can see my drawing here, what I'm going to do is just draw like a real quick view. So if this was our original length, right, of steel, so the length of steel, what happened is due to the thermal expansion, steel has shifted up a certain value, right, which we just determined was, 120 times 10 to the negative 6 length, whatever our length, original length was, right? And this one deflected up as well because it was symmetric loading. So the copper, right, if we look at the copper, that was in the center, and we determined that it shifted up more, right? More than the steel. Because this was 170 times 10 to the negative 6th multiplied to the length, right? Verify those answers, and 170, yeah, so that was right. So what we want to look at is these two lengths right here. So if this is the height of the copper and this is the height of the steel, what we want to know is what is this difference, right? And just real quick, what we can do is just simple math. It's just 170 times 10 to the negative 6 minus 120 times 10 to the negative 6, and that equals 50 times 10 to the negative 6 multiplied to L, right? So this delta L here, the little red one I did, this distance here, is that. And that's important. And the reason why is because now that we've determined the thermal expansion, how much they increase, right? Now, that was the first step. The second step was what happens when we apply 40 kilonewtons of loading due to this rigid plate. So think about what happens. If I took a rigid plate, and we've already got, due to my deflection drawings here, if I've already got this piece, this level, this height, and I apply a load, a rigid plate that's even all the way across, it's going to hit the copper first, right? And then that plate is going to shift down on the copper until it hits the steel, right? The copper will be carrying the entire steel plate, or the rigid plate, I'm sorry, until it deflects all the way down and touches the steel. So what we want to determine is how much of that 40 kilonewtons does the copper actually carry, right? So to be able to figure this out, what we can do is take this distance, right? And we can use our relations. The change of length of copper is going to equal, right, our force multiplied to the length divided by our area multiplied to the modulus of elasticity. And again, all of this is for copper. So then what we can do is say 50 times 10 to the negative 6 L equals the force that's applied to the copper, the length, the area of the copper, modulus of elasticity, and just dividing our L's out from both sides, those cancel. And solving this, because the area and the modulus of elasticity are known, we can then solve this and find our force that's applied to the copper is then going to equal 10.45 kilonewtons. Okay? So this is kind of like a intermediate step. This isn't the actual answer because it actually asks to determine the forces carried by the copper and the steel cylinders. You may want to look at this number and think to yourself, okay, well, that's the force that's carried by the copper. That's not entirely true. That's the force that's carried by the copper until that rigid bar hits the steel. There's still another step that we need to do, a couple of steps left to do. So this isn't the answer, the final answer for the copper. It's the intermediate answer. So the next thing we need to do is determine how much of the load, right, is going to be applied to both the copper and the cylinder, because this 10.45 kilonewtons is just on the copper prior to it hitting the steel. Okay, so we'll say the 40 kilonewtons, right, that we originally started with minus the 10.45 kilonewtons is then going to equal what, 29.55 kilonewtons. Okay, so this 29.55 kilonewtons is going to be applied evenly between, well, not evenly, but it's going to be applied to both the steel and copper. This 29.55 kilonewtons is going to be distributed between both the copper and the steel. So how do we determine this? Well, we can look at our relationship that when they deflect, the copper and steel, so if we go back to this drawing here, once the steel bar that's here deflects this distance, right, and it touches and it's on all three members, at that point there will be an even deflection between them. It looks like more like stress. It was delta, which is delta L. So we can then make a relation that our delta of the steel is going to equal delta of the copper, or to stay uniform, it's delta of the steel equals delta length of the copper. So we can then use our formula, and it says delta length of steel equals delta length, steel equals delta length of copper. So the force that's applied to the steel, length of steel divided by area of steel modulus of elasticity of steel equals copper, length copper, area copper, modulus of elasticity of copper. So then we can solve this in terms of the force, say, I don't know, the force of steel equaling some constant multiplied to the force of copper, right? And again, because these L's are going to be the same, right, they will cancel out. And so we're just left with the force of steel equals the force of copper multiplied to, if you plug in the values for the areas and the modulus of elasticity, you should end up with 1.15. So this we can identify as, I guess, equation 1, right? So what was equation 2, right? Equation 2, well, if you remember what I wrote a little bit just here, this 29.55 kilonewtons is going to be distributed between both the steel and the copper. So that means that the force of the steel plus, or the force applied to the steel plus the force applied to the copper is then going to equal our 29.55 kilonewtons. So here we have equation 2. Two equations, two unknowns. Be able to solve it pretty readily, and you should end up with a force of the steel, or force applied to the steel, is equaling 15.8 kilonewtons, and then the force applied to the copper is then going to equal 24.20 kilonewtons.